So now when we're dealing with inverse functions, we are going to algebraically find the inverse function, if it exists. Now, generally speaking, when you're algebraically going to find an inverse function, the restrictions are already set up so that it is 1-to-1, but not always the case. Algebraically, find the inverse function of f of x is equal to 2x minus 3. We're going to follow a series of steps through here, but we're going to hit on one of those themes. One of those themes is that the x's and y's switch. So really, the first thing that we're going to do is replace the functional notation with y. This really does nothing, but it helps out the thought a little bit later. Now we're going to make it an inverse. We are simply going to switch the x's and the y's. So replace x with y, and then y with x. So at the moment right now, we have an inverse. Now what we're going to do is we're going to isolate y. So I'm going to write this in a different color, and we're just going to isolate y to put it back into functional form. So perhaps I'm going to go over here, and I'm just going to rewrite this. Pardon me, that was incredibly wrong for a bit. So x is equal to 2y minus 3. I'm going to add 3 to both sides, and then I'm going to divide both sides by 2. So in other words, I have y is equal to x plus 3 over 2. And this is my inverse function. And since it's my inverse function, I am going to use functional notation again. So really, starting anything in purple up until this point, it was really just isolating y. And then what we're going to do is replace or reintroduce functional notation so that we know it's an inverse function. Now, I think that this result makes sense. If you take the original f of x, what did you do to the input? You multiplied the input by 2, and then you subtracted 3. Well then, how do we undo multiplying by 2 and subtract 3? Well, we add 3, then divide by 2. I think that actually makes some intuitive sense. But please do not jump and make any conclusions about inverse functions off the top of your head, because you will be surprised. All right, next one. G of x is equal to 3x squared minus 4, where x is greater than or equal to 0. Now, keep in mind, I'm going to be looking at my positive arm here. My vertex is going to be at 0, -4 of my parabola. That's g of x. So I'm going to be taking a look at my positive arm, and that will have an effect later on. Now, for more thorough analysis, you'll be taking a look at this in grade 12. So again, I'm just going to replace my functional notation with y. Next thing I'm going to do, I'm going to create my inverse. By writing x instead of y and y instead of x. So this is what we have here. This is my inverse. Now I'm going to isolate y. So I'm going to switch colors to purple again. And anything in purple, I'm going to try to isolate for y. So switch x and y. All right. So really what I'm going to do here is I'm going to add 4 to both sides. And maybe just out of convenience, and I like it better when y is on the left-hand side. So I have 3y squared is equal to x plus 4. I'm going to divide both sides by 3. And now I'm going to take the square root. Of both sides. Now, normally we consider both positive and negative roots. However, remember what I said, that I'm only considering the positive arm of my parabola. There was my original parabola, g of x, and I had vertex 0, negative 4, and I was only going to include the positive arm. Well, this directly correlates to including only the positive root. So really, the solution to this, I would only consider the positive root. Now, here's a weird thing. You notice my root sign doesn't go all the way down to my denominator. That is an irritant of teachers. You have to make sure it goes all the way down to the bottom of 3, just to be crystal clear. So this is my inverse function, so I'm just going to reintroduce my functional notation. So the inverse of g of x is equal to the square root of x plus 4 over 3. Now here we can say x has to be greater than or equal to negative 4. Just as the domain to restrict to make sure that my radicand is non-negative. All right, this one is a lot of fun because it is very, very troubling. I'm going to start this off. So I'm going to algebraically find the inverse function. I'm going to replace the functional notation with y, just to make it sort of nice and easy. And then I am going to replace x's with y's and y's with x's. Here we are. Here's my inverse function. If I were you, I would press pause. Isolate y. Good luck. And when you're ready, press unpause, and you'll learn something in algebra of value. All right, I'm coming back. So hopefully you press pause, give that a shot. Anyways, this is baffling to people because often there are, I'm going to multiply both sides by y minus 1. Now, why am I going to do that? I'm not too sure, but I just have a feeling. So I have this phenomenon where I have two y's, and it's really troubling. And if I do that, I'm going to multiply, redistribute this, and see where this is going. So, and then it seems like I'm going to get a bigger and bigger expression. So I have xy minus x is equal to y. Somehow I need to isolate y. So right here is my inverse. I made it my inverse. Now I need to algebraically isolate y. And it just seems like this is turning into a big disaster. However, and then I get an incredibly wonderful idea. Any ideas yet? That's right. I'm going to factor out y. If you factor out y from the left-hand side, you have y by itself. Now, this step, you're probably able to figure out how to find or isolate y by itself. You can just divide both sides by x minus 1. Now, I'm just going to put the restriction that x can't be equal to 1. So this is an interesting scenario. Number one, this should be a good learning experience. Notice it's the problem of having two y's. So what do? You should probably bring them over to one side, and it's going to take a few steps of algebra. It took me up until there to isolate y to all the y's to one side. And once you have all the y's to one side, try factoring out the y. And it leads to this scenario. Now, another thing that you guys may or may not find terribly interesting is that here's h of x. Look closely at h of x. Now I'm going to write the inverse of h. And wouldn't you know, the inverse of h is just h. So inverse functions are kind of interesting that h of x is a function, but its inverse is the same function. So this is a function that undoes itself. That's pretty neat. Also, h of x, what can be said about the graph of h of x? Well, the graph of h of x and the inverse are going to be the same, but moreover, another theme, remember that, is that h of x and the inverse are going to be symmetric about the identity line. That is really, really interesting. Anyways, I'm sure there's just one more video.